Then I've got another question, right? And this question is also based on the photoelectric effect, also question 11. Already you can see a trend that all questions 11s are photoelectric effect. So it says the threshold frequency, remember that is Fo, of cesium. Now cesium is a type of metal and we have potassium. Already in your mind, you need to know that different metals will have different frequencies and different metals will have different work functions. This is because we need different frequencies to actually emit the electrons from these different metals. So do not always look at it on one side and say it's going to be the same. It will be different. So cesium and potassium metals are given in the table below. If they give you a table, only use that table to answer those questions. Here's my metals, then I've got my threshold frequencies, the minimum amount of energy required to emit an electron. I can see they've given me values. Remember, frequency is measured in hertz, and that is why I've got Hz. Now, the first question says, define the term work function. Now, they're saying term. In the previous question, they said define or what is meant by the photoelectric effect. So already you're seeing a little pattern, what they do here. So they can either ask you to define or what is meant or give the term. They usually like asking the photoelectric effect, the threshold frequency, the work function. So make sure that you do know these definitions off by heart. But in this case, the term for the work function for 2 marks, let us answer that question. So this will be 11.1. 11.1, they want us to define the work function. And the work function of a metal is the minimum. Very important word. The minimum energy needed to eject. Remember, electrons don't leave metals, they are ejected. Needed to eject an electron. Electron from the metal surface. From the metal surface. Okay, that is our first definition. Now let's see what our next question says. So that is 2 marks. Remember, we don't fail definitions. We get 4 marks for definitions. So 11.2 says, which one, now they only wrote 1 in capital letters. If you name 2, you might be penalized. Which one of the 2 metals, which 2 metals are they talking about? The ones in the table. In the table has the higher work function. Remember, the work function we were just told is the minimum energy required to actually eject an electron. Now, what they've told us is the threshold frequency. The threshold frequency is the minimum frequency that is then required. So between these 2 metals, which one will have the higher work function? Now, I can see that the threshold frequency for cesium is 5.07. Right? But for potassium, it is 5.55. So it means that the work function for potassium is higher than that of cesium. So our answer, they just say give 1, and then they ask us to give a reason. Remember, if they're asking you to give a reason based on something, don't say because the table says so. No, we're doing the photoelectric effect. What is determined by the work function? It is the threshold frequency. So use the correct terminology to support your answer. That is what the examiner wants to see. They want to know whether you know or understand the relationship between the work function as well as the threshold frequency. So for 2 marks, you get an answer for actually identifying between the 2 and giving a reason. So let's do that one. So for this one, and this is 11.2, they said give 1. So you can say potassium, because potassium does have a higher work function, potassium. And they're saying give a reason. Now, the threshold frequency for potassium is greater than the threshold frequency for cesium. And then just to add on to this, if you look at the work function, remember it is directly proportional to FO. So if you need minimum amount of energy, and then with the minimum amount of energy that's needed, we can see that For potassium, it is much more greater than that of cesium. That is the minimum amount of energy for potassium that's required to emit an electron. So it will have a higher work function for that specific metal. We got a mark for identifying the one, and you get a mark for giving a reason. Now remember, let's say for example, you got the identifying wrong, but you do get the explanation right, then the examiner will give you a mark. It means that there was just a little bit of an oopsie there. Now, let's continue with the next one. It says, the simplified diagrams below show two circuits. Now, they've named it A and B in bold letters. It means continue naming them A and B. And they contain photocells. The photocell in A contains cesium, a cesium metal plate, while the photocell in B contains potassium metal plate. Already from the information given, we know that potassium will have a higher work function than what cesium will have. Now we can see something very interesting with these ones. They both use ultraviolet light. Now remember, even though they are using the same light, right? Maybe it even has the same frequency. However, different metals will have different work functions, even though the light is the same. But remember what we said, the different types of metals are not the same. So they require different amount of energies to actually emit the electrons out of the metal. So in this case, I see my cesium metal, my ultraviolet light. Now we learned about ultraviolet light in grade 10, so now it's just an add-on to what we're doing. So now it says the ultraviolet light with the same intensity. Remember, intensity just means more electrons will be emitted with the same amount of kinetic energy. So the same intensity and wavelength, when we talk about wavelength, we talk about lambda. We find lambda from our frequency. So the same wavelength of 5.5. So both of them have a wavelength of 5.5 times 10 to the 7 meters. It is in the correct SI unit. Is incident on the metal plate in each of the photocells, and the ammeter. Now they bringing in a little bit of electricity. Remember, an ammeter, learning from electricity, measures current. So an ammeter in circuit A registers a current. So we have an enough current. Now let's see what we have to answer. By means of calculation, so they don't want you to explain, they want you to give a calculation. For 3 marks, you are going to get a mark for using the correct formula. So by means of a calculation, determine whether the ammeter in B will also register a current. Now, how do you go about a question like this? I want you guys to take a clear head and then think about it. I want to make an example, then I'm going to go back to the photoelectric effect. If you are seriously hungry during break and you have 5 rand to buy a pie, that is the maximum amount of money that you have to go buy a pie. And you go to the tuck shop and you say, can I please buy a pie? And they say, ooh, but a pie is 7 rand, right? The minimum amount of money required for a pie is 7 rand. It means you do not qualify to get a pie. It's the same thing that these electrons are doing. If this metal does not get the maximum amount or the minimum amount of energy to emit the electrons are not going to move. They actually require enough energy to actually be emitted. So remember, you have to have, when you get to the tuck shop, you have to have minimum amount of money to buy a pie. So if you do not register, or you do not have that minimum amount, you cannot get what you want. Same thing. So in order for us to actually see whether we can get a current or not, we need to calculate whether the ultraviolet light with this wavelength is going to produce a work function or frequency big enough. Remember, this is the minimum amount of energy required. So if we get a frequency that is lower than this, it means that we do not qualify because this is the minimum that's needed. Anything less than that means, oh, no, we are not getting a pie. So it is exactly the same thing. The electrons need to have enough of that energy to actually continue moving forward. So let's see how we're going to do this one. So this is 11.3. So we must determine whether the ammeter is going to get a reading. So I'm going to do it in 2 ways. The first one, remember, we can look at frequency, which is lambda. Now this is for B. Remember, C is the speed of light, which is 3 times 10 to the exponent 8. Now I want to look for the frequency to see the frequency of the ultraviolet light. What is it giving me with the frequency, the minimum frequency that is required? The lambda, I was told, is at an intensity of 5.5 times 10 to the negative 7. Now I know that for B, we have to have 5.57. So finding F, remember I want to get F alone, so I'm going to say 3 times 10 to the exponent 8, divide that side by 5.5 times 10 to the negative 7. If you put this in your calculator, you find that the frequency is 5.45 times 10 to the 14 hertz. Now, I can already conclude to say that the frequency of the UV light is actually less than the threshold frequency of potassium. Remember, potassium is identified as a K. Can you see that the frequency that the ultraviolet light is going to give is 545? However, the frequency required for potassium to be emitted from the metal is 5.55. So 545 is much less than this. So no. This electron is not going to move. Remember, you need to show by calculation. And then, it's also nice to actually show that you understand what is happening here. So that is the one way that you can actually show it. Another way that you can do it is to say, find the work function, right? If you can find the work function, remember, that is the minimum amount of energy required to emit this electron from the metal. If we can find the work function in correspondence with the energy, we can then say whether these electrons will have enough energy to actually be emitted from the metal surface. So again, the same thing. You have to have a little bit of money to get the pie, but if the pie does not reach your standard, you are not getting a pie, right? So now we're going to do the other way. So I'm just going to say OR here. So I can say E is equal to HC over my lambda. I want to find E. H is 6.63 times 10 to the negative 34. C is a constant, which is 3 times 10 to the exponent 8, all over. The lambda that was given by the UV light is 5.5 times 10 to the 7. I want to see how much energy this will have. Then I get 3.6164 times 10 to the negative 19. Remember, energy is measured at the SI unit for joules. However, if I look at the work function, the minimum amount of energy that these electrons should have, I'm going to have 6.63 times 10 to the negative 34, which is Planck's constant. The frequency of the UV light is 5.5 times 10 to the negative 7. If you put this in your calculator, you get 3.68 times 10 to the negative 19. Work function is then also in joules. So I just want us to conclude. I just want to use a different color here. I want to write here. So this means, remember, my work function is the minimum amount of energy that's required. I can see that my work function is actually greater than the energy that these electrons will have. Look at this. The minimum energy required for the electron to leave the metal is 3.68. However, these electrons only have an energy of 3.61. So it means the energy required to actually move is greater than what the energy will have. So no, my darlings, the ammeter will not register a current. And then that is then how we will tackle questions like this. Now, it does look like it's a mouthful, but probably what you've already seen, the formulas don't change. There are so many constants that you need to remember. But something that you need to keep in mind when you are doing the photoelectric effect is that most of the time there's 3 ways in which they can ask you. They can give you a scenario and you have to find everything. They can give you a table or they can give you a graph. Now, I've already shown you the table. Last week we did scenarios, and in this week we also did a table. So make sure you understand the constants and what works where. And always remember, the electron needs to have enough kinetic energy to move. If the photon does not give it, then the electron is a very bored electron and it's not going anywhere. Thank you so much for joining me in today's show. I really hope you understand the photoelectric a little bit more this time. Thank you so much for joining me. I am Tobile King, and I'll see you next week.